Arctic Ocean now, after if you count Mosaic along. So this, I will show a few slides of these first preliminary data, and this is all compiled by a whole bunch of people. I put a few names here on the first slide, but it's really the whole team of Ecolite, and in fact, some of the teams, Team Eco on Mosaic Lab 5 that have contributed to this week, to do this work in various extents. So as we probably all know, the Arctic Ocean is changing very fast. And just as a quick reminder from this ice barren scenery that was imagined by Caspar David Friedrich in 1824, it's actually not a true picture. It's what he thought the Arctic would be like based on what he saw in the Baltic Sea. But this is how the Arctic kind of used to be. We are moving to an Arctic that has a shorter sea ice season. The sea ice is thinning. And by doing so, it's becoming more dynamic. And at the same time, the physical oceanography changes in the Arctic Ocean as well, mainly by advecting more heat with the Atlantic water inflow into the Arctic Ocean proper. And all these processes have profound impacts on how the ecosystems of the Arctic Ocean are going to function in the future. Now, one key aspect of the Ecolite project obviously is the role of sea ice and how sea ice changes in this context. In Ecolite, the starting point of Ecolite was to look at the biogeochemical role that sea ice takes and the role how it controls primary production and then also secondary production in the Arctic Ocean, and then to find a way to understand how the system works today, and then use various modeling approaches to actually maybe get a better grip of what we can expect in the future. The changes that we are going to see mainly have to do with the thinning and more dynamic part of the sea ice. And the angle at which Ecolite is going in here is that this is mainly triggering a big change in the light regime of the Arctic Ocean. And the light impacts not only the primary producers, it also impacts the zooplankton and other parts of the faunistic part of the ecosystem, because these organisms react indirectly because they react to the distribution of ice algae and phytoplankton, but they also react directly to changes in the light climate because zooplankton, for example, adjusts their vertical distribution in the water column according to light. So the objectives of this small module of Ecolite about which I will talk today, which is the AZFP, the Acoustic Zooplankton and Fish Profiler, that we put out in the Arctic Ocean, was to investigate the effect of the changing under ice light field on the abundance and vertical distribution of zooplankton, and then to analyze the interaction of zooplankton distribution with hydrography and food availability, and obviously also sea ice conditions. And last but not least, actually evaluate how an autonomous AZFP could actually function in the Arctic Ocean. Because that's the point here. We have to be out there in this environment that is really hard to access, and therefore it's really desirable to have a system that can record data in the absence of humans and ships. And this would actually be a very nice tool if we could use them more in the future to see how the Arctic Ocean ecosystem is going to change. Because for some time from now on, although the ice is going to be thinner and the season is going to be shorter, there will be enormous amounts of ice in the Arctic Ocean. And the only way to assess what the ecosystem is doing is to use either icebreakers or autonomous buoys that can monitor parameters of that ecosystem. So this is a sketch of how, in an ideal world, we thought the setup would look like of such a buoy system. In the foreground of the picture here, I think, do you see my mouse arrow? Yeah, okay. Yeah, so here you see a drawing of our AZFP buoy with a dome on the top side of the ice, which has the Iridium transmitter and a camera built in. And then through the ice, we have a hole, and underneath we deploy the transducers and a couple of other sensors of the AZFP. And this AZFP buoy is not alone. It is combined with a set of other buoys. And in our in this case of Ecolite, we added a light buoy, a so-called IBOB, to it, so that we could have detailed measurements of the light climate. Attached to the AZFP, we also had a fluorescence probe, CDOM, measurements, and salinity and water temperature at the ice-water interface. So here's a picture of how it looked in real life when Mario Hoppmann and others deployed the device at the during leg 5 of Mosaic. On the right-hand side, you see the device. And remember, there was a comment, I think, in the chat at the beginning of today's workshop that at least we're not landing on Mars. I think this device looks a little bit like the things they put on Mars. However, I also realized that data transmission seems to work better from Mars to Earth than from the North Pole to Bremerhaven. Maybe something to work on. So obviously we have a GPS positioning device on there. And as I said, the fluorometer and a couple of internal devices that help us monitor the quality of the whole system, basically the health of the system, practically constantly, because this system communicates with Europe via Iridium, and it's possible to look at the status of the system, but also to apply changes to the measurement, the way it measures, or the interval at which data are taken. Then, as I mentioned before, we had put an ice-tethered bio-optical buoy, a so-called IBOB, also nearby this AZFP to get a very good view of the light field and a couple of other ecosystem parameters. However, that thing stopped transmitting pretty fast. So those data we don't have at the moment, and we will never get them. But there is a backup thanks to the tremendous amounts of devices that have been deployed on Mosaic, and many of them actually being left, just like our AZFP buoy. We do have a backup that gives us some data on water column properties with the thermistor change, with CTDs, and with light measurements above and under the ice. And this is a map of where on the Mosaic ice flow the system was deployed. I think the spatial scale goes from very large here on the left side, where the approximate composition is depicted at the end of leg 5. And then if you look, those of you who are familiar with the Mosaic flow, you can see that there was a huge array at which they deployed buoys. And then here in the lower right corner of this array, this is where the AZFP buoy was deposited together, luckily, with the other light and physical oceanography buoy. And since that time, so that was September 2020, until today, these are data until the beginning of February, but until today, the system with our AZFP buoy has been surviving and has been drifting across the Arctic Ocean, just like Polarstern did a year before. And this is really nice because from Polarstern, we already have a hydroacoustic data set with zooplankton proxy, and also the species composition coming along with that. And now we have repeated basically this drift again with the AZFP buoy. And now if we go into some first data, this is all raw data, not only very basic processing. You can see that the first thing that we could see already in the autumn data, that's data from September to November 2020. There was this conspicuous line in our acoustic data. And I think those of you who work with hydroacoustic should be familiar with it. And this is coinciding with changes in the density of the water. So it's a pycnocline, in fact, that was ranging at approximately 20-meter water depth. And then, of course, we ask ourselves, what do we do with such a signal? What does it tell us? Is it just the density surface of the water, or is it actually also something that has more zooplankton associated with it? And we looked into data from Mosaic, which again is raw data that was kindly provided by Nicole Hildebrand from the Loki, which is an imaging zooplankton profiler. So it takes images of zooplankton whenever they are there. And this is only a depth profile of the raw images, so it's not accounted for double photos and things like that. But it's a proxy of zooplankton abundance in a way. And you can see that actually at this pycnocline here, there is also an increase in zooplankton. So these two features, they fall together, and that makes a lot of sense biologically, of course, but it's a nut for us to crack because it's difficult to separate the two in the hydroacoustic data. And I'd be really happy to hear some advice from the folks around here. And then what we could also see is we then made a very rough treatment to the data. We just cut out that piece that contains the pycnocline to look more at the distribution of zooplankton above and below the pycnocline. And we could see that with the sunset with the beginning of the polar light through a twilight period, the backscatter intensity seemed to increase in the very top layer above the pycnocline, whereas below it's remained relatively shallow. And we looked at these processes or at this feature actually in combination with the sun, the height of the sun, and also with the moon cycle. And there also seems to be a little bit of a periodic vertical shift in the few days that we call the twilight period, where there's actually a day-night rhythm in the high Arctic. Below, you see the whole data set from September through November again. And you can see also here that at a certain a couple of days after the sun has set, we see an increase of backscatter above the pycnocline. And if you zoom into this region, we see here on top the incoming light in blue and the light transmitted through the sea ice in red. That's PAR. And then in the middle, we see the spectral light transmission under the ice. And below, we see the intensity of the backscatter signal integrated over the top 60 meters. And here, it also looks like, if this is not something done with calculation, this is just me eyeballing some kind of running average through the whole backscatter data. You see that there's an increase in intensity in this top layer, 60 meters, that coincides with the reduction of light, the transition from polar day to polar night.
5 minutes.
Was there a question?
No, I was just saying 5 minutes left.
Oh yeah, we'll be in time. And then you could also see other features from those data. Here in the top row, we see backscatter at 125 kilohertz. Again, raw data, not cleaned, not processed. And you see these features here that occur repeatedly of intensified backscatter right underneath the pycnocline. And we looked these data in combination with the data from the physical oceanography buoy that we have nearby, and could actually see that, first of all, there was turbulence at the beginning and the end of these blobs when the thermistor change was moved up and down. And also we see a change in the temperature and salinity profiles, which all indicates that this could have been an eddy passing underneath the ice flow, or vice versa, however you see it, and that this eddy was associated with increased abundance of zooplankton, possibly. And that I found was a quite exciting feature to see. And I think it shows how valuable such autonomous tools are to, over a long time, monitor the ecosystem there, because the chance to hit those eddies with a ship that is just doing an expedition is quite limited. This is a map of the drift of the buoy during these eddy transition, and you could see that it's basically the same eddy that was surpassed a couple of times. So in conclusion, this AZFP buoy allows holistic observations of the coupled physical biological system. It captures transition phases when we are usually not there, like the transition from polar day to polar night, and vice versa. We are of course excited of what's going to happen now. And also it shows particular events that might not be so easy to actually catch with traditional expeditions. The system, as it is designed now, is able to transmit data almost in real time, which is a big advantage. We can see how the status of the system is, how well the batteries are doing, and so on. And we can actually manipulate the measurement regime remotely from a warm office at home. And this has been done several times, and so far has always been successful. There are, of course, challenges. First one is that wildlife might be attracted to them and might mistake them for a basketball. And we have had our experience with previous versions of this system, but I think the dome construction that we have now seems to be pretty stable. And of course, the physical environment is not nice in these regions too. We can get, the sensors can get icing, and the ice can do its own motion, and things like this are constantly in danger of being destroyed, of course, and there's nothing one can do about it. Communication is sometimes an issue, but that might be solved in the future. At the moment, we are just simply struggling with the narrow bandwidth that Iridium offers and the high costs that are associated with that. So thinking towards the future, we are constantly discussing of what we can learn from that and how the next generation of such a device should look like. First conclusion is it always must float, because the ice can always go away and these things are expensive. So you want to keep a chance to recover them. And I think this system is actually floating, but I don't know if all the parts are floating. We should improve, again, the resistance against polar bears. But then with the next generation of Iridium Certus, data bandwidth might not be such an issue anymore, and it will in fact allow a much wider range of measurements that we can take, and also a higher resolution of our sampling. Of course, it's always nice to have more such devices to mitigate the risk of losing one, but also to capture the natural variability in not only in terms of time, but also in terms of space. And last but not least, to combine this and other systems in big arrays that allow a multidisciplinary monitoring of the system in kind of the same, in a quasi-synoptic way.